Electric motors get pretty hot. This is a pretty good example of an electric motor. This is an outrunner motor, which means the outside of it spins, and you've got the stator on the inside, which you can see here, and the bell on the outside, which you can see here. These electric motors are great for small scale remote control aircraft, but on a larger scale, they generate a lot of heat. The stator and the bell will both have heat being generated from them due to a loss of energy within the stator and the bell. The bell gets hot because of these things called eddy currents, which heat up all of the magnets. The stator gets hot because a lot of electric current is flowing through each of the copper wires. Even though there isn't much resistance within these wires, it still builds up, and this heat can and will burn out motors if you're not careful, especially when you push them to their limits. One way to cool down these stators is by flowing air over the coils. You can see in this design, you've got air that can pass through into the stator and out through the bottom. This is called heat drag in an aircraft. One way I thought of combating heat drag was to thermally connect the spinner, which is usually mounted on the outside of a prop, to the stator. This is beneficial because there's less effort given into getting air to circulate through the actual motor. Another idea is connecting the propeller thermally to the bell. The propeller and bell system are usually connected anyway, and by having heat vent through the propeller, which is moving very fast through the air relative to the bell, it will create a cooler outside, and that will also influence how cool this is.
This is my motor design. I designed it in an on shape. It has a spinner that dissipates heat from the stator through the stator mount. It has bearings that separate stationary components from moving components, and it has a propeller that is directly attached to the outer bell housing. Everything in the design is mine except for the blue parts, which are a modified existing motor, and the red parts, which are bearings that I can't really manufacture myself. Hopefully this design allows me to create the motor using a 3-axis CNC machine and manual lathes. And I'm pretty excited. Let's get to building. So first, let's modify the parts we need to modify from the original motor. This is me spinning down the bell. Also, not in the imagery is me pulling the stator off of the existing motor mount. And here's the final product. It looks pretty good, down to 20 millimeters, which is exactly what I needed. Next up came machining all the smaller parts. I machined most of them out of 2-inch billet stock aluminum. This is because aluminum is really conductive while also being really easy to machine. Some of the fixturing would have been hard in the CNC mill, so I used some of my friends' manual lathes and manual mills to tap and drill some holes that were inconvenient and make a part that I didn't get to make while I was at college. One of the hardest parts about this project was definitely machining the propeller. It took a lot of setup and ops to do, and it needed to be done because there was no propeller on the market that had the geometry in the center of the prop that I needed. I used hot glue for some of the setups because it reduced the chatter and increased the amount of stability in the middle of the propeller. During the middle of some G-codes, I clamped it down in different areas to reduce chatter as well. This worked really well, and I'm really proud of the surface finish I was able to achieve on the propeller first try. Let's go! Assembling the motor was rather straightforward. I first got some of the outer assembly done. This involved doing some lathe work and truing up some of the surfaces that the bearings seated on so that they would be nice and precise. This worked really well as I was able to fit the bearings to each individual place they were going to be mounted. Next, I tapped the holes that the propeller screws into on the bell and cleaned out any remnants of aluminum or steel that had been in the bell. After this was probably the most challenging part of the assembly, which was getting the stator all together. The stator assembly is very complex and requires wires to pass through the bearing, and you have to glue the bearing in without making the bearing not spin. I then made a plate that I could screw the motor onto so that I could test it. This is the finalized stator assembly. It looks really cool in my opinion. This is the outer bell assembly. It slips right over the stator assembly, which makes it really easy to assemble and really easy to deconstruct if you want to look at the internal temperatures of the stator while you're doing testing. This is the finalized pusher propeller. You can see I put 3 M2.5 bolts in there to fasten the propeller to the outer bell housing. After really quickly testing that it spun without a prop, I put a prop on it. Alright, I'm going to get some protection. During this testing, it was making a little bit of a rattle noise, which I eliminated by cleaning out the bearings as they had a little bit of aluminum dust in them.
Full throttle.
I bought and used a thermal imaging camera throughout this project. It helped me gain insight into what was actually happening thermally to the motor. On the left, you can see an example of some of the images I took during my testing, and on the right, you can see the conductive heat transfer between the stator and the spinner. Finally, here are my motor test results. I tested using several different conditions, one with the spinner on and one with the spinner off. You can see I took a lot of data points at different times during the trials. I recorded temperatures for every minute for 10 minutes. I tested at 10 minutes because it struck a good balance between being at equilibrium while also being timely. I used a voltage of around 24 for all of the testing and would modify the throttle position to get the total watts that I wanted. I tested at several different wattages as the efficiency and heat output are different at different wattages. Using a log regression for all test runs shows that running the motor with the spinner attached almost always results in a lower motor temperature. The only anomaly to this was the 63 watt condition, shown in black, where the ambient temperature of the room could have changed or the efficiency of the motor could have changed significantly between the spinner on and spinner off configuration. Thank you so much for watching. I really hope you enjoyed, and I hope this inspires you to make something yourself or explore the world of electric propulsion.